recording. Okay, so welcome to the SPACE webinar. This is going to be our last talk in the season 2. So today our speaker is Sabine Süsstrunk. Let me do a short introduction of our speaker. So Sabine is a full professor and director of the Image and Visual Representation Lab in the School of Computer and Communication Sciences at the EPFL Switzerland since 1999. So her main research interests are in computational photography, computational imaging, color image processing, and computer vision, machine learning, and computational image quality and aesthetics. Sabine has a very long list of awards and affiliations. So she is currently a fellow of IEEE and ISNT. She is the president of the Swiss Science Council, SSC. So without further ado, let's welcome the speaker, Sabine. She is going to talk about opponency revisited.
Thank you very much, Jane, and thank you very much for the invitation to all the organizers. It's a pleasure to be here. Well, to be virtually here at least. So the topic of my talk is opponency revisited. And, you know, let me just take the punchline ahead. I'm actually going to talk mostly about color opponency and not political opponency. Well, most of the time, but there is actually going to be a joke about it. So, you know we're virtual, but that doesn't mean that I cannot actually ask you a small question and we'll do a small exercise. So I'm just going to pause them for a minute and let you think about it. So So my quick question is, what color is code value 25500? Now, as you're all in image processing, you probably know that very well, and the answer is going to be red. So if I communicate to my device driver, the triplet 25500, it will activate the red LED in your display. And that's what you're seeing now on your screen, like this. But which red? If I now insert yellow bars between the rectangles, did you notice, or can you actually see and perceive how the color is changing? And now if I put the blue bars, you can actually even strongly see that we're looking at totally different reds. So this visual experiment, by the way, was made famous by Stephen Chabelle of the University of Chicago, well illustrates that color is a percept. While it depends on physics, i.e. the light emitted by your screen, it's also processed by the human vision system, and that in a highly nonlinear fashion that we still do not fully understand. So let's go back to physics. As you are all very well aware, we credit Isaac Newton with the first published color theory, at least here in the Western Hemisphere. Excuse me, I will just excuse something. I need to reorganize my screen a little bit. Okay, this is fine. So in 1666, Newton observed that the spectrum of colors exciting a prism is oblong, even when the light ray entering the prism is circular. In other words, the prism refracts different colors by different angles. This led him to conclude that color is a property intrinsic to light, a point which has been debated by none other than Johann Wolfgang von Goethe. You might remember Johann Wolfgang von Goethe, for all of those of you who suffered through German classes in high school or college. He's a very famous poet and writer. So Goethe proposed a color wheel to explain how colors relate to each other. There are neighboring colors and opposing colors. So here are neighboring colors, here are opposing colors. He included also with his color wheel aesthetic qualities. So the purple kind of color over here is beautiful. Red is noble, yellow is good, green is useful, blue is mean, and dark purple is unnecessary. Now the overreaching quadrants are reason, understanding, sensuality, and fantasy. So he published this in 1810 in his Theory of Colors. The original German title was Farbenlehre. And he describes his views on the nature of colors and how these are perceived by humans. And he wrote, and it is where I'll quote, and you can actually read it, so I'll stop for a minute. And he continues. So end quote, and I thank Wikipedia for the translation. So slightly passive-aggressive, wouldn't you say? You know, I said I'm not going to talk about politics, but it reminds me a lot about the political discourse nowadays that people are right and wrong. Or maybe it can also be some scientific discourse that things, current researchers say something is right or something is wrong. Well, we can, you know, again, take the punchline ahead. It turned out that both are correct and both are right. So how do these two different color theories relate? You know, as you all know, visible light is part of the electromagnetic spectrum, ranging from about 400 to 700 nanometers, where the cones, i.e. the spectrally selective photosensitive elements of the human eye, exhibit sensitivity. In other words, this is the range our visual system is sensitive to. Now, if you separate the spectrum into individual parts, say from 400 to 500 nanometer, we perceive that radiation as first purple and then bluish, from 500 to 600 as green, then yellow, then red. The combination of all these wavelengths at more or less equal power gives us white. We exploit that in imaging in the form of color encodings, where each color image file has, at each spatial location, 3 code values assigned to it. One for the red channel, i.e. how much red is in that location, one for the green channel, and one for the blue channel. So this additive combination of all these, of these triplet, gives us actually the color at that pixel location. Now, sRGB is the most common color encoding that we have today in photography, and it corresponds to a camera output. But there's also a different color encodings like XYZ, which is based on color matching functions, and LMS, which actually represents the cone space of the human eye. However, in parallel, the idea of opponent colors was also pursued. Whereas Goethe argued with Newton, Hering was the one who challenged the young Helmholtz theory of trichromatic color, which I just explained. So Hering's representation, and subsequently also Mansell's and others, show, you know, how colors actually will relate to each other, and they're much closer to Goethe's color wheel than Newton's rainbow. Their observation was that certain colors just do not mix. They are opposed to each other or opponent to each other. So take the example of red and green. Have you ever heard of a reddish green or a greenish red? That just doesn't exist. These are colors that just do not ever mix. However, we have heard of a yellowish red. We call that orange. Or of a greenish blue, which is teal or turquoise. So the same thing can also be said about yellow and blue. There's no yellowish blue or bluish yellow. So as such, red and green, as well as yellow and blue, are actually opponent colors. It took until the middle of the last century until researchers investigating retinal processing in the eye actually came up with a physiological explanation of why the two color theories are both correct. Besides the cones, drawn here as the, as these kind of dome-like structures on top of the illustration, we have additional cell layers in the retina that highly nonlinearly process the input signals before passing them to the brain through the ganglion cells. So while the young Helmholtz trichromatic color vision, and thus Newton's viewpoint, is certainly correct on the level of the cones, what is passed on to the ganglion cells that carry the visual information into the brain is a comparison of the signals captured by the cones compared to the signals captured by neighboring cones. This concept is called receptive fields, and they explain color constancy. So these are these receptive fields. So it was found that we have several types of receptive fields, spectrally non-selective ones which distinguish between black and white, and spectrally selective ones distinguishing between red and green and yellow and blue. So in summary, it is actually the contrast between these colors that is communicated to the brain, not their absolute values, which is actually captured by the cones, but it's now communicated to the brain. And then took another few years until the 1980s, when finally Buchsbaum and Gottschalk mathematically related to two color theories. They showed that the principal component analysis of the sensitivity functions of L, M, and S cones, so these are the S, M, and L cone sensitivities, result in an achromatic, here illustrated in white, and two chromatic channels, red, green, and blue, yellow. Here the green, red, if you so will, and here the blue, yellow. This decomposition is due to the symmetry and positivity of the covariance matrix, as both L or all L, M, and S sensitivity functions are always positive. These channels do correspond to the measured receptive field properties of the ganglion cells. This also shows that the case for color, a decorrelation process is a possible explanation of the retinal functions. Now, remember, decorrelation is a way to remove redundancy. So from information theory, we know that efficient information transmission can be defined mathematically in terms of minimizing the channel capacity required to transmit the information. So we have approximately 2 orders of magnitude more photosensitive cells that capture the lights, that's the rods and the cones, than cells that transport signals to the visual cortex. That would be the ganglion cells. So it actually makes perfect sense that there is some kind of information reduction, decorrelation process taking place in the retina. So we have in imaging many color encoding based on opponent color principle. Many ways to transform from additive color to opponent color. One of the most famous, of course, is YCRCB, which was first used in television encoding and now in image and video compression. For the sake of our research that I will present next, I want to introduce CIELAB, C-I-E-L-A-B color space, which you might or might not be that familiar with. It was developed by the Color Standards Organization CIE, Commission Internationale de l'Éclairage, based on a psychovisual experiment by McAdams. And he did actually an experiment on just noticeable difference of colors. I'll spare you the details. It's a very famous paper. You will find it anywhere if you're interested. But what happened was that CIELAB was developed to actually make these just noticeable difference ellipses, as they were in the experiments, as uniform, circular as possible over the whole color space. In that representation, perceptual color differences then can be expressed as Euclidean distances. If it is true and all these just noticeable differences would be all circular or, in a ball, of course, if you think about 3D, and more or less the same size. By this optimization, turned out that the CIE-LAB color space became an opponent color space, where on the z-axis, you will basically have white versus black. On the x-axis, you have green versus red. And on the b-axis, you have yellow versus blue. So the white versus black axis is also called the L-axis or the lightness axis. So as already basically introduced, in this color representation, perceptual color differences are Euclidean distances, and they can just be calculated as shown here, of the delta L squared plus the delta A squared plus the delta B squared, and taking the square root thereof. Now, I put a little note there that, of course, CLAB is not a perceptual uniform color space in the way I'm implying it here. For our experiments, it was good enough, but there are some other distance metrics that are used nowadays if you do measure color, like delta E 94 or delta E 2000, which take into account the non-uniformity or the of the CA color space. Now, it is also representation using the original delta E. A delta E of about 1 is considered a good approximation of a just noticeable difference in simultaneous matching. So how do we use this, effectively use this contrast, this correlation, this opponency concept in imaging? One of the very famous examples, of course, is video compression. And I will not talk about this because that's not the work we've done. I want to talk about several other kind of application which are just as useful, and we have employed these concepts quite successfully. So the first one is saliency or salient regions, or salient region detection. So what are salient regions? Salient regions are the regions of the image that stand out with respect to the rest of the image. So they're visually conspicuous. And there is this concept of task-independent saliency, which is a low-level vision concept, which basically says independent of what's in the image or the semantic meaning of the image, you're basically going to have a certain amount of contrast, certain amount of things who stand out with respect to the rest. And here in this example, it's absolutely clear. You're going to look at this red pin first before you see the other pins, because it is different. It has contrast compared to the rest. And as it's semantically, independent would be the same thing for a blue ball between yellow balls or something, or whatever example you can actually think of. In contrast, task-specific saliency, or conversely, maybe I shouldn't overuse the word contrast. Task-specific saliency occurs when you do something specific, when you're actually asked to do a task. So if you look at this image now, low-level saliency would probably be that you see the rider in the background or the horse in the background first, because the color is standing out with respect to the rest. Now, a task-specific saliency would be if I would now ask you to count the number of faces in this image. And I'm going to give you a minute to actually look at this image. And I still think that you probably relatively soon start seeing a face here maybe, and a face here, and a face here. I'm going to let you count for a few seconds how many faces you can actually find. So now you probably should be up by about 8 or maybe about 9. Well, I'm going to give you the link. You can go double check, but I'll show you the results now. Currently, the maximum faces found is 22, but you're more than happy to go and actually see if you can find even more, and then go to that website and actually report how many you did find. So anyway, let's come back to the salient region and salient region detector. So what we wanted to do is you find a method that gives us actually a map that tells us where an image, an object is salient, or which object is actually salient. This, of course, is now for low-level vision. We're not talking about semantics here at all. So this is an example of images and example of salient region detectors. So we would ask ourselves, actually, what should a good detector do? Well, it should, of course, emphasize the largest salient objects in an image, but it should give us all salient objects in an image. And then it should uniformly highlight the whole salient region and not just give us the edges, of course. But it still should give us sharp edges of where that salient object stops. It should also not actually, capture high frequencies arising from texture noise or, some kind of encoding artifacts. And it should efficiently and fast output full resolution saliency maps. Not just, and this is actually something for those of you familiar with the saliency literature, you know, but there's many kind of maps that have this kind of fuzzy, you know, points where it actually, they're all kind of developed to match the eye tracking experiments that are done to actually establish ground truths for saliency. And with eye tracking, as you know, it's never quite as precise, and you see these kind of blobs, and that's good to actually identify which object is salient, but it's not good to actually do something, do some processing with it. So where did we start? Well, we do want the edges of the salient object, and then the difference of Gaussian filtering is a proven and true way in image processing to find edges in an image. So we just started from there. By the way, they're also a little reminiscent of the receptive fields in the retina. So we defined saliency as the absolute difference of the center Gaussian and the surround Gaussian. The biggest question, of course, is which center Gaussian and which surround Gaussian. So, well, as you do that with, in the lab, of course, you never put this in a paper, but you just try. And here is now an illustration of increasing center sigma on the y-axis and increasing the surround sigma on the x-axis. And you can kind of see, okay, we have here excellent edges. Up here, we don't have the edges anymore. But up here, we actually have the full salient objects highlighted, whereas here we do not. And, as a consequence, the best result, of course, is here at the lower right-hand corner. This is the one that fulfills our criteria, and it corresponds to a very small sigma in the center and a very large sigma for the surround. So our saliency detection algorithm is nothing else than taking an image. Keep in mind, this is, of course, a task-independent saliency algorithm, so low-level vision. And we calculate first the image average, which is actually similar to convolving the whole image with a Gaussian filter of infinite sigma. So the very large surround. Then we first blur slightly with a very small, actually, sigma, the image to actually remove noise and high frequencies. So this is kind of a pre-processing step. And then we actually take smallest Gaussian, the single pixel, and calculate its LAB value. We also calculate the LAB value of the mean or the average of the picture. And then our saliency is actually nothing else than the absolute difference of these two Gaussians, the very big one of the surround, the tiny one, i.e. our individual pixel, and that gives us a salient indication, and we can then create a saliency map. Now, for those of you, paid attention before, this is nothing else than a delta E. So this is perceptual delta E calculation that we're doing here for actually detecting saliency, totally inspired actually by this contrast encoding of the human eye. Oops, yeah, sorry. Here is the delta E. So what do we use the salient region detector for? We can use it in image segmentation. We used it in edge detection. We use it in document correction. We even combined it with some task-specific saliency to find text in natural images. We used it for image resizing. And here's this kind of an example where on the left, you see the original seam carving, and the right, you see the saliency improved seam carving. Same thing here. Whatever you want, right? There's a lot of things you can do. Now, of course, I have to actually kind of say, well, color is not the only measure of contrast or of dissimilarity in an image. So you can have also, of course, texture orientation, you can have size, different sizes, different movements, all these kind of like low-level concepts are also have an influence in saliency. And that has, of course, been exploited in the last 10 years in many kind of saliency applications. Now, it also basically goes beyond, we just talked about low-level saliency, but it also goes to mid-level saliency, where the semantics start to play a role, where you actually look at object orientation, size, and appearance. So there's really a lot of research done in the last decade on this topic, and not just using classic methods that I introduced just now, where basically a simple delta E, but also many deep learning methods. I'm just showing one of our recent papers actually as a placeholder here, where we, took an overall global saliency method and then encoded appearance dissimilarity and size dissimilarity to actually improve saliency. But that's just a placeholder. There's many excellent works in this. It's still not totally resolved. So there's still actually lots of good research that can be done, because we can still not totally predict what saliency is, especially high-level saliency. I mean, the saliency that actually, what is important to you. And that depends, of course, on your experiences, on your likes and dislikes, on your own kind of, personal semantics, and that we are extremely far away from actually modeling. So there's still going to be quite a bit of research in the future, as you will see on this topic. So let me give you another example where we have used opponency very successfully. And that's actually in our superpixel, supervoxel, and adaptals algorithm. So we have actually published 3. First one was SLIC in 2012, then SNIC, its non-iterative version in CBPR 17, and then actually an adaptals version that 2018. Let me just walk you through this very quickly. So first of all, what are superpixels? So superpixels are pixel clusters of an over-segmented image. So on the right-hand side, you see basically these clusters. So each superpixel has a cluster of some pixels. The advantage of using superpixel is that they actually coarsen the image representation, and they reduce complexity, because you've actually pooled in the image statistics within a meaningful region. So, of course, this is somewhat of a, toy example, but as you can see, right, you do not need to encode every pixel of this sky. You can pool some pixels together because it's basically the same thing. And so you can reduce, in general, you can reduce the image statistics by 2 orders the number of superpixels compared to the pixels, is usually about 2 orders of magnitude less than, as I said, the pixels. So they're also really convenient primitives for other algorithms to build upon, and they have application depth estimation, body pose model, image segmentation, tracking, independent if you're using deep learning or not. So there also have been very many applications where you use superpixels as pre-processing step in afterwards some deep learning based method to do one of the applications I just mentioned. Now, of course, there are plenty other superpixel methods. Ours is not the only ones. I'm just showing you some. Felsenwalben-Huttenlocher is a well-known one. That's a graph-based one. Levenstein published one. So there's plenty of ones to do. So we're not the only ones. But of course, I will present ours. So our SLIC and SNIC, and actually also our adaptals method, are based on K-means in a 3 to 6 dimensional space of color values and spatial coordinates. So if you do supervoxels, of course, you have 3 spatial dimensions. If you do pictures, you have 2 spatial dimensions. If you do black and white, you just have 1 color dimensions. If you do color, you have, of course, 3. So somewhere in between 3 by 6 dimensional color space will actually do K-means. Then we normalize this color and spatial distances, using the maximum distances within a cluster. And so our distance metric is as follows. So you have Euclidean distance in spatial dimension, So this is your spatial proximity term. And then you have a color proximity term. And this is in CLAB. And this, of course, looks very familiar. It's the delta L squared plus delta A squared plus delta B squared, i.e. your delta E. So the number of clusters, by the way, is the number equal to the number of superpixels that we get. Now, and here are some results of SLICs. It's also kind of shows you what happens when you vary the number of clusters, many clusters, less cluster, and very few clusters. And especially when you use very few clusters, you might see right here that you're not actually capturing always the edges of the object anymore. Here I give you an illustration of SNCC. SNCC is non-iterative, so you actually can deal with this. It's somewhat faster, and it also deals. SLIC had a problem with orphan pixels, which you needed to kind of remove at the post-processing step. SNCC does not have that problem, but that's not that important for now. And then we have the last algorithm is adaptals, still the same kind of proximity term. Adaptals is an algorithm that actually has different sizes of superpixels based on the complexity of the image region. So if you have a low frequencies where you can really pool many pixels that are similar together, you actually have larger regions. And if you have small or a much more varying image region like distress, you basically now see that the adaptals, as it says, adapt to the image content. Let me show you again illustratively with a little video how this actually works. So here we're actually starting in the center and then use again the same distance, color distance metric, where we kind of calculate, go distance, distance, distance up to a threshold, and that then starts at the border of a given adaptal, a new adaptal. So we're looking actually using, again, perceived color differences. How far away from a central pixel can we go before that color difference hits a predefined threshold? And then here is another example. So again, what I said, as mentioned before, there are pre-processing steps for a number of applications in imaging, right? I mean, this is segmentation, this is detection, also in medical imaging, it's remote sensing. We use supervoxels once in a beauty, estimating the beauty of video content, whatever you want, right? And it's still an extremely popular algorithm. Here is the, it's a list of imaging domains where our first superpixel algorithm was used. It shows basically the citation count per field according to Scopus. So besides computer science, like computer vision, you have remote sensing, you have material sciences, you have physics and astronomy, you have medicine. You actually have quite a number of citation mathematics. Under other, you find economy and social sciences and whatever you want. So, but to a certain point, yes, I want to show off a little bit, but to a certain point, I also just want to, re-emphasize the point. It is an extremely simple algorithm. It deals with perceived color differences in, if you will, your intensity axis and some spatial Euclidean distance in the spatial dimension. But it works. It doesn't work always. It is a pre-processing algorithm, but it is actually quite efficient and quite, or very efficient actually. And here I just wanted to, again, make the plug. Simple is good. It doesn't have to be complicated. It can be very simple. And maybe then afterwards in the question, I can actually tell you the story of how often this paper was rejected before we could actually publish it as being too simple. But anyway, we're not going to go there. So now, At this point in time, I wanted to talk about our work extending opponency into the near infrared. Well, near infrared is actually a radiation we cannot see, but funnily enough, opponency also works quite well in this domain. But I actually realized I would run out of time because I do want to show you how we're actually using opponency and machine learning. And so I do want to talk about some of our newer research, but I do put opponency here in quotes, right? I mean, it doesn't actually have anything to do with color opponency, but more the concept of decorrelation or maybe disentanglement if we actually use the machine learning jargon. So but it's still this idea of decorrelation, getting away from, what can we actually do? And so let me show you this work, Editing in Style, Uncovering the Local Semantics of GANs. This work was actually published last year at CVPR. And of course, this is one good thing, maybe the only good thing that came out of these virtual conferences, is that we all had to produce videos. So let me just show you actually the video we produced. So, so we all know that GANs can achieve state-of-the-art image synthesis, and that you can, edit between the GAN outputs easily. Now, we actually found a method to not just edit generally, but edit locally. Now, with either the eyes or the nose or the mouth by interpreting between two GAN outputs. And this is actually not just limited to faces. It can be basically limited to any kind of data set that you know. So let me actually walk you through this. So this paper is, about changing the local semantics of an image. We have two, a reference and a style target, which are two outputs of a GAN. In this case, this GAN was trained on the flicker face data set. And it can be, we show basically that these deep generative models like PGGAN, StyleGAN, and the recent StyleGAN 2 learn a representation of objects and object parts. And then we can actually disentangle these object parts in semantic meaningful parts. In other words, objects can be, split apart. So because somewhere in this encoding of the GAN, there is a mouth of the person or the wheels of the car. And then by manipulating then just these semantically meaningful activations, we can actually change the image. So based on that observation, we basically performed spatially localized semantic editing. Now, why did we even come up with this idea? Well, we basically published a couple of years earlier, DCCV, some matrix factorization on 4 CNNs. So again, we were basically, we wanted to know where is actually what encoded in a CNN. So this was work of Ido Cohen's, former PhD student of mine, who is now at Google, where he basically developed a method to extract semantic object and objects part from the deep layers of a pre-trained network, such as VGG or ResNet, trained on ImageNet. So what he did, given a few images as input, here I'm going to show the example with 3 images. We take the feature maps A from a deep layer, one more time, this was actually the last layer before the fully connected ones. And we stack them in a matrix, on which we perform non-negative matrix factorization. The resulting U and V matrix have then, of course, K dimension. We choose which rank K. We can then reshape the matrix to a tensor, and we can produce K sets of heat maps. And these heat maps actually show a very, very good overlap with semantic parts and object parts. So let me give you an example. Here we can see the results from K1 to K4. So this is the original of this gymnast. So K1, as you can see, the heat map basically encompasses the body. With K equal 2, we are already separating the limb from the body. So here legs and arms, the body is still blue. With K equals 3, you actually separate legs and arms. And then K equals 4, you can see the bar. And very kind of similarly, you can do it for the elephant the whole body, elephant upper body, legs, elephant, ground here, even upper body, middle body, legs, and so on, and here on the ground. Now, one of the things I do want to emphasize is the network has never seen these images before. So it was not trained on gymnasts and it was not trained on elephants. So this is actually the important part. We can just take a few images, we run it through, and then we do this matrix factorization on these activation layers. So this is just another trained network and another data set. So we then did some experiments, and we could also show that our deep feature factorization, basically outperformed the state of the art in both image retrieval and localization of the region of interest within a set of retrieved images. So now, same kind of concept, but now we analyze the layers of a GAN generator network. So instead of non-negative matrix factorization that worked relatively well because we had the ReLU network and it was all positive, we actually now use Spherical K-Means. And so we test multiple layers and different Ks. So here is, for example, the layer 32 by 32, K equals 2. And you can already see, okay, it distinguishes between faces and backgrounds. K equals 3, okay, we can already separate mouth and eyes out of the images and the backgrounds. And with K equal 10, we get a good separation of all the facial features. K equal 25 is an oversegmentation. And, similarly to 128 by 128, K equal 25 doesn't really make, it does separate actually the noses and the mouth, but you have like cheek and separation, and you have throat separation you might not want to do. So we found actually that the lower layers have greater control of shape and the higher layers have greater control of texture. And this intermediate layer of 32 by 32, which I actually showed you, the faces are really spatially distangled, or the facial parts are spatially distangled into semantic objects. So then we labeled the cluster. We had to do this manually, but you only have to do this once. And you can do this offline per GAN and data sets. So we just used a batch of generated images, about 200, and then we qualitatively evaluate the cluster masks at different layers and different Ks, and choosing the most semantic setting. And here I'll show you the, and then we actually go and find the best overlapping channel for these clusters. And this is the channel now for eyes. This is the one for nose, and this is now the one for mouth. So, and now by manipulating these channels, i.e. by interpreting these channels between two outputs of the GAN, we can actually now do this localized editing that I showed you before. And I just show it to you one more time. Look at the eyes changing, the nose changing, and the mouth changing. Now, our method also extends to unaligned reference and target images. And here is the example of the bedroom. So we can change the bed, we can change the pillows, or we can change the windows. And these are not aligned. As you can see, the reference and the target images are not aligned. So the beds are not all in the same position. And of course, you can also do it for, in this case, the cats, not just the bedrooms. You can look at the eyes, the snout, and the body. So now, think about it. So not only can we now generate images, we can actually manipulate these images, and we can interpret it between those two. But of course, you're kind of going like, okay, CVPR 2020, it's a lifetime ago. It was last year. Now, what about this year? Well, this year, and I'm just going to give you a quick preview of what we're working on now, is we don't actually need 2 pictures anymore. We can just take the GAN output, just take 1 image, and actually now manipulate, for example, the nose, the mouth, the car, the horse, and even do little details that I have not ever seen before so far. We can actually change the eyebrows. Then, of course, the bed you've already seen. We can change the sky, and we change the dog. And this is all using different data sets and actually different GANs, different big GAN, style GAN 1, style GAN 2. So this is what the difference a year makes. So I hate to see how photorealistic we're going to be next year. So that's about the 50 minutes that we talked about before. So let me get to the conclusions. I hope I kind of could motivate to you that the simple kind of concept of opponency, color opponency, contrast, disanglement, dissimilarity, is an interesting concept, and it has actually played a central role in our research, or in the research of my lab. I've always been kind of curious to see what's all behind it. What can we actually get out of these systems? What can we, what can this bring us? This kind of like, and it's all related, it might not, from an English grammar point of view, all mean the same, but it is all related in the imaging kind of thing. It's just kind of this difference, what is different. But the real inspiration has, of course, been that this is what our human vision system does, right? It does actually react to differences. It does disentangle if you use machine learning talk. It does decorrelate if you use mathematical talk. And we just can exploit this in numerous ways to improve visual computing. Okay, so that brings me to the end. Let me, thank very much. The work I've presented is actually the work of 2 of my former and 1 of my current PhD students, or rather Krishna Ashanta of the Saliency in Superpixel, Edo Collins of the deep feature factorization, and again, semantic editing, localized editing, and Ezan, who is in his first year of a PhD, who has actually pushed this work forward. But I also would, of course, want to thank everyone in the lab, in IVRL. Everybody participated in some way or form in this work, be it by discussion, giving feedback. And I really want to see that, emphasize the research is a teamwork, and it's the exchanging of ideas that bring our field forward, and not just individuals. So thank you very much.
Thanks a lot, Sabine. So I have a question really related to your first slides about the red color. Mm-hmm. So do you know if there's any neuroscience explanation of how we perceive this difference in the red when there's a background contrast?
Yeah, exactly. It's a very local adaptation, right? Mm-hmm. So you have a color next to it, and that pushes actually your percept somewhere else. So think about chromatic adaptation. You're all familiar with chromatic adaptation, right? We adapt to the color of the light. Well, there's something similar going on locally. So you have this local kind of adaptation, I think also your eye is jumping around all the time. So you're going back and forth, and you have this local kind of adaptation that is, I'm simplifying this a lot, but it has much to do with this idea of, seeing something pushes it actually forward. Now, in addition, though, the difference in color, depending if you're on top or at the side, surrounded by another one, that I do not know if there's an explanation for it, because that's just, So the simultaneous contrast we know, the localized simultaneous contrast we know, but why there's a spatial difference, let me put it this way, I don't know if there's an explanation for it. There might be an explanation for it.
I see. And the continuing question is, if you insert this image into, say, a neural network system, can it tell the difference between, in I know the digital code for those two reds are the same, but can they perceive it as different red as we perceive it?
It's a good question. I don't know. I've never tried it, but you gave me now an idea of something we should actually try. But what will you train it on, right? That's a little bit of the problem, right? What's going to be your ground truth? What are you going to train on? Oh, this is a bluish red and this is a yellowish red. I mean, how would you even set up a neural network system that, and see, here's actually the one thing that is so fascinating about this whole thing is what we perceive and what we measure is not the same thing. And then making a correct metric or a ground truth of something you perceive but you can't really measure is damn hard, right? And so a lot of the thing is, this is why we're using so many psychovisual experiments, actually, at the end, okay, is this a better picture? Is this not a better picture? Coming back to saliency, there's about 5 or 4 different metrics that people use to say, okay, my method in predicting saliency is better than the others, and none of them were worth anything, right? Same thing with the GAN output, how photorealistic is it? Well, we use this inception score. Well, it doesn't mean that this image is photorealistic, it just gives you an average overall. And so there's many, hand waving, to be honest, in this kind of field, because how do you measure percept, right? And I mean, I find it actually extremely difficult, right? We have done our part of hand waving, saying, okay, this metric's good enough to actually predict that we're doing well, but it is a lot of hand waving. And I mean, I find it a very, very interesting research direction. It's kind of been abandoned lately, but this kind of, image appearance models have kind of gone away, but they should come back, right? Because we still don't have a good one.
I think that's related to this question on the anonymous attendee. So could you give some performance benchmarks? How long will it take to process a 10-second video? I think maybe it's related to your GAN model.
Well, again, we just use images, right? This is not... these are not videos. So could it be with the super voxels or something like that? No, I don't know. Because GANs, here the GANs, oh, okay, well, no, I can't. I mean, in each individual frame, if you will, right, is very quick, right? So 10 seconds video wouldn't take any time. If you think, okay, I would want to, do every individual kind of frame. Most of these algorithms I've shown are actually, if not real time, close to real time, because they're so simple, right? I mean, there's not much calculation at all. The SLIC is not totally real time. SNCC, because it's non-iterative, is faster, right? So if it comes to that one. But I to be absolutely frank, I would have to refer to the paper or refer the anonymous, a question asker. Look at the papers and you can actually, we have the numbers reported, how long it takes for which size images.
Okay, so so are there any other questions? Sorry about my noise in the background. Okay, so thanks, Sabine, again for the wonderful talk. I think it's a very interesting topic, like perception and also opponency for computer vision, photography problems. So this is our last webinar for this season. So we plan to have another season 3 starting from fall semester. So we will keep you posted and send out all the information, and we will have. There's another anonymous question. So have you, Sabine, have you tried your methods on animated movies?
Yes, the super voxel picture, or which method?
Didn't specify.
Okay, so what it is, what I skipped is kind of like the super voxels can be done in any kind of video and also in any kind of animated kind of thing. So that works. If we've tried the GANs, the GAN editing on the feature editing, okay, that's the thing. Let me, oops, sorry, I just wanted to, this is not what I wanted to do. We're still screen sharing. Let me just call this one back up again. No, we didn't. But we have now tried it at least on these paintings. They're not quite as, let me put it this way, they're not quite as abstract as animations yet, but they're already kind of go there. So that would be something else we would have to try. But that, the answer right now is no. We have not used them on animated moving. Yes, I also think it has a great potential. So hopefully, so of this one you'll hear more about. On the other hand, think about also, this is of course totally scary, right? Oh, I don't like, the picture of my great-great-grandfather, he's such a dour look. So I'm going to give him, a nose job or something like this, And this is, of course, the easy one. But the application of all this is, of course, in advertising, right? Think about how relieved all these ad agencies are if they don't need to have any model releases anymore, and they can just, I mean, that's just around the corner, I assume.
Mm-hmm. Okay, so next, Eric Bennett has a question. Eric, do you want to speak with Sabine, or I can allow you to unmute you? Or let me see.
Okay, I see this. Okay, I'm an engineer working in medical imaging. Recently, we are adding additional information from intensity. We collect phase or frequency information. Do you have any advice for mapping these to color? Yes. Well, yes and no. The first question I would ask you is kind of like, what's the goal of the visualization? What do you want to show? And then you're mapping it to color that whatever you want to show or emphasizes is in highest contrast to the rest. So one of the things is never take these pre-computed false color bars. They're just nonsense, right? So whatever you want to, do you have phase or frequency information? What frequency range is the most important? And then you're mapping this to something that is visually conspicuous with the rest, and that is you choose the color you want, and you make opponent colors, because all the rest you might want to do in a monochrome. You might want to highlight something red, and all the rest you do in a monochrome green or maybe bluish. And that's what you're going to do. So, but it's always, these kind of visualization tasks are always extremely dependent on what exactly you want to show. What's the most important? And then, of course, this is now a simple one thing, there's one range that is salient. You might have multiple salient in the sense of what you want to highlight things, and then you have to think a little bit about it. Hope that answered your question. Okay, how much is the GAN approach is useful for indoor localization? Not quite sure I understand that question. So indoor localization in the sense of localizing where a robot is indoors, or indoor localization of changing, the bedroom or the... So this localized editing means it's just, we're editing localized parts of an image and not the whole image. So, or the positioning, I would say not at all. Mm-hmm. I mean, yeah, I cannot see how the positioning actually, how it, well, it is a good thing, because they're thinking about it, but then you would have to have, it would not be useful, because one of the reasons is this changes the same, a localized part that has the same semantics, but not the same localization. So in face images, usually the eyes and the nose and the mouth are always at the same localization, but you've seen, with the bedroom images, the beds can be different localization. So it changes the pillows of the bed, even if they're different localization, but it does not give you the positioning of, even if you would know one, you could not find the same positioning in the others. You would find a different positioning. Or maybe that's exactly what you want, right? If you want to find all the pillows where they're positioned, that could be used. For that, it could be used probably.
Okay, so it looks like we have all the questions answered. So let's thank Sabine again. And as I mentioned, there will be a season 3, and just keep posted. And I will see you guys next semester. Okay.
Thank you to all who stuck with me, and thank you to Jane and